Okay, here we go again. So we are looking at hyperbolas. We're going to take a look first at the definition because we talked yesterday. Actually, been talking this whole unit about the importance of the definitions. They really help us with word problems. Word problems, a lot of them are written with the definition in mind. So if we look at this definition, it's the set of all points of the difference. It's the difference of whose distances from two fixed points are constant. So what we're looking at here is, if you recall from yesterday, our ellipses, it was the sum of them were the same, right? The sum of the distances were the same. This is the difference. And I'm going to attempt to draw with this. Let's see. So if we take this point here and we would look at the, add these two segments to, actually we're subtracting, it's the differences. So if we subtract these, we'd get a number, a constant. Any other place, say we go here and we do the same thing and we subtract those distances, we're going to get the exact same number. It doesn't matter where we're going from, we will get the same number. Okay, so it's the differences, which I think is kind of helpful for us because with a hyperbola, those equations are written with a subtraction. So it kind of makes sense that their definition would include a subtraction. It's the differences of the distance instead. Like on the ellipse, it was the sum of the differences. Okay, I'm just trying to help you to match the definition to which conic section it comes from in preparation for our applications. Okay, so that's pretty important to note. So let's look at some other things besides just the definition. There are two orientations for the hyperbola. One, if you'll notice, the x fraction is positive. This is a hyperbola that opens along the x-axis, or horizontal axis at any rate, not necessarily the x-axis, but a horizontal axis. We then have another kind. This is where the y fraction is positive. So these hyperbola pieces open along a vertical axis. So that's something to keep in mind. Now, I'm just going to point out it's not always the first fraction. Sometimes these are written in a very strange way, and maybe this subtraction fraction would be first. So just please note that it's the fraction that is the positive fraction carries the weight for this particular conic. If y is positive, then it's going to be on a vertical axis. If x is positive, it's going to be on a horizontal axis. So it's just something to keep in mind. So notice that these two look very much like an ellipse equation that we studied yesterday. The only difference really is this is a subtraction instead of an addition. That's the only difference. We still have our h and k. We still have our a squared and b squared. A squared and b squared mean something different in a hyperbola, and that sometimes students get mixed up. So in an ellipse, a squared was the biggest number, right? In a hyperbola, it's not necessarily the biggest number. That has nothing to do with which one is a and which one is b. It has to do with which fraction is positive and which fraction is negative. The positive fraction is the fraction that gets the a. Notice how both of these, the positive fraction gets the a. The negative fraction gets the b. I mean, that's how it's separated. And the size of a and b have absolutely nothing to do with which one is going to be a and which one's going to be b. It just has to do with which one of them belongs to the positive fraction. Okay? So our criteria is just that a and b are positive. Hyperbolas also have a little helper equation, just like ellipses do. This c squared equals a squared plus b squared. So notice how the hyperbola main equation, standard equation, has a subtraction sign, but its little helper equation has an addition sign. They're always opposite. All right. Then we have the axes actually have names. On an ellipse, it's just the major and minor axis. But in a hyperbola, they have names. It's the transverse axis and the conjugate axis. So the transverse axis is the axis that connects the hyperbola pieces, the main axis. This is called the transverse axis. And sometimes on your word problems, they'll just give you the length of the transverse or conjugate axis. They'll just say that. So we need to know what that means. So transverse axis is the axis that connects the two hyperbola pieces together. The conjugate axis is kind of this imaginary axis over here. It doesn't really connect any of the curve together. It just helps us with our structure. I call it a scaffold. It helps us to draw our hyperbola. The length of the axes are 2a and 2b, just like the lengths that we found with ellipses, just 2 times a and 2 times b. Those are the lengths of those axes. And the last thing that I want to talk about actually is the asymptotes. So sometimes students find it very difficult to find the asymptotes. So let's kind of walk through, how do we do that? How do we know how to find the asymptotes? First of all, I want you to notice that these asymptotes, no matter which version of the hyperbola, have one point in common. These are two lines with one point in common. They have the center point in common. So that's the point that we use to write the lines. We use the center point. And we're using, yes, one of my favorite equations of the line. Actually, it is my favorite equation of the line. Y minus y1 equals m times x minus x1. I mean, that's a great equation. And so our h and k will come from the center. Now, do you have to write both asymptotes in one equation? No, it's just easier that way. Some students really want two different equations. You certainly can do that if you want to. But since they both contain this point, hk, and we can do a plus minus and the slopes are identical except a plus minus, it's kind of convenient not to write two different equations. It's kind of convenient to just leave it as one. So that's my preference, is to leave it as one. So we have our h and k, that's our center. Well, how do we get our slope? That's kind of confusing. What do we do there? So you can read the slope off of the equation. That's certainly possible. You can also count the slope off of your rectangle that you're going to draw when you graph these. Let's talk about how we read it off the equation. So we know that slope is rise over run. Right, it's rise over run. And rise, I mean, that's a vertical thing. That's like height. That's like y. And run is like x, right? That's like horizontal. And if you look, notice that this top number is going to come from underneath the y fraction. This top number, the rise, is from under the y fraction. Look over here. This top number is from under the y fraction. That's where it comes from. And the bottom number, the denominator, is from the run, or the horizontal movement, which is from what's under x. So the run comes from whatever's under x. So that's how you can read it straight off of the equation, and you don't have to count, the squares or whatever in your box to figure out what the slope is. All right, so questions so far. Are we okay with the concepts? Okay, so I just have a couple of different problems. Let's kind of go to our first one. This is this one right here, actually. This is the one that we have on our notes, and so I just want to walk through it. We're going to complete the square. Notice how we group the x's together and group the y's together, and then move the constant to the side. Okay, so we're grouping the x's, we're grouping the y's, and we're moving the constant to the side. Okay. Once we have that done, we want to start thinking about how are we going to complete the square. With the pair of x's, that's going to be easy. I don't have a coefficient to deal with, do I? But the y's, I have a -4 here. I have to factor out that -4. So we factor out the -4, and that leaves us with y squared minus 4y. Okay. Now we're going to go through the completing the square process. Half of 2 is 1. 1 squared is 1. Add 1 to this side. Add 1 to this side. Okay. Half of 4 is 2. 2 squared is 4. I add 4 to this side. But did I really add 4 to this side? I didn't, did I? I actually subtracted 16 from this side, didn't I? And if I subtract 16 from this side, I have to subtract 16 from this side. Okay. So now we're ready to factor. And the x's factor to be x minus 1 squared. And the y's factor to be y minus 2 squared. And this is what we have going on right here. So we know it's a hyperbola because it's got this subtraction. And we need to divide everything by 4. Right? Let's just divide everything by 4, and this is what we get. We would get x minus 1 squared over 4 minus y minus 2 squared. Okay, so here's our equation. All right, any questions about that first part? Okay, we have our equation of our hyperbola. So now let's identify what's a and b and c. So a, I'm going to get from my positive fraction. That's where it comes from. And so the square root of 4 would be 2. That's my a value. B, I'm going to get from my negative fraction. And that's a 1. So the square root of 1 is 1. C, I'm going to get from my helper equation, right? Which is c squared equals a squared plus b squared. So 4 plus 1 would be 5, right? And so c would just be root 5. Because it would be c squared equals 5, so c would be root 5. Is everybody okay with finding the a and the b and the c? We okay with that? Okay. So now let's look at the center. The center is hk, so it's at 1, 2. We read it right out of the equation right here, 1, 2. So let's go over here and let's start creating our hyperbola. Let's go ahead and plot the center. So we're going to go to 1, 2, and we're going to put a point. There's our center point. I think it's interesting that the center point doesn't have anything to do. I mean, it's not on the curve at all. It's just kind of sitting in the middle. It's just sitting in the middle there. It's the center of it, but it's not on the curve. It's in the scaffolding part, the part that we use to help build a fairly, a good sketch or good accurate sketch of what our hyperbola would look like. So there's our center. Our vertices, we're going to use our A and go 2 spaces to the left and 2 spaces to the right. These are our vertices at negative 1, 2 and at 1, 2, 3, at 3, 2. These are where our vertices are. Okay, so let's go through and let's finish the graph of this. So what we do is we basically have already written what our vertices are. Our co-vertices are along the conjugate axis. We're going to go up 1 and down 1 right here. So those would be the little, and they really don't call them co-vertices, but this is where my conjugate axis is. It's right here. It's right on this line right here. Okay, my conjugate axis would be 2 spaces. And so we draw a little rectangle. The reason we do this is really just to develop a scaffold for where to draw our hyperbola. That's all it is. It's just a structure to help build the hyperbola. And the reason that it's really beneficial is because the asymptotes travel through the corners. The asymptotes start at the center and they travel through the corners of this little rectangular box that we're drawing. And so that really gives us a good idea of how wide to make our hyperbola. If we didn't have these asymptotes, we'd have no idea. I mean, we would have, whether is it gigantic, is it really narrow? I mean, we wouldn't know. So the asymptotes are really a big help when we're drawing our graph. So we draw in our asymptotes. And then we just start at our vertex and we're going to mold the graph along the asymptote. So on either side, we're molding it right along the asymptote. Okay. And lastly, what we would do is we would plot the focus points. So let's calculate what are our focus points. Our C was root 5. So if I'm going to start at my center and I'm going to add root 5. Right, so root 5 is what, between root 4 and root 9, so somewhere between 2 and 3. So 1, 2, so we'd be somewhere between 2 and 3 right here on either side. Now this is an important note for us, and in word problems, sometimes all they do is tell us where the focus points are. If the focus points fall inside of the vertices, am I going to have a hyperbola? No, I wouldn't. Would I? Wouldn't I have probably like an ellipse? I would have an ellipse. Notice how these focus points fall outside the 2 vertices. In a hyperbola, they're outside the 2 vertices, so that really helps us with word problems. Okay, so we would do 1 plus or minus root 5, because that's what we do. We would add C and subtract C. And it's just fine if you want to write these 2 points as 1 point when you have a crazy radical like that. That's okay. Much easier to do. It certainly wouldn't be okay to write the points as 1 when you have just regular old numbers, but with a radical, it's perfectly fine to do that. 1 plus or minus root 5, 2. That's both focus points right there. So the equation of the asymptote, let's write that out. So we have our y1, y minus y1, and our y1 is 2, equals, let's skip over the slope for right now, x minus x1, and our x1 is negative 1. Oops, over here, we're the center. Our x1 is 1, so it would be x minus 1. Here's our center, 1, 2. So I have 1, 2. Okay, so that's what we have going on. So now let's talk about the slope. How do we do the slope? Well, we have two options. We can go up to our equation and read it off of our equation. The number underneath the y, the square root of the number under the y, should be our numerator. Right? So square root of 1 is 1. That's our numerator. The square root of the number under x should be our denominator. The square root of 4 is 2. Perfect. Another way that we can do it is by going to the center of our graph and counting rise, run to the corner. So I rise 1 and I run 2. And that also gives me my slope. So you have a couple of different ways to find your slope. Are we okay with that? Okay. Lastly, let's look at the domain. So our x values are going to go from negative infinity to negative 1. And we're going to include negative 1 because it's actually on the curve. Then it continues on. The middle part, all that part that's included with the scaffold, that's not part of the curve. It's just what we use to build it. So we're going from 3, over here from 3 to infinity. That's our domain. And our range is going to be from negative infinity to infinity. Okay, how are we doing on that question? Is everybody okay? Okay. We have one other question to do. That's where we're going to write the standard equation with the information that we have. We have a center and a vertex and an asymptote. So let's go down to that. Okay. So let's focus just on this portion right here. Let's look at it says write the standard equation of the hyperbola with center negative 2, 4, a vertex at 6, 4, and an asymptote, and they give us the equation of the asymptote. Okay? So this is the problem that we're working right here. So let's plot our center. Our center is at negative 2, 4. So here's our center. And then we're going to plot our vertex. Our vertex is at 6, 4. And we're going to put our vertex here. Now this is how I would find the information that I needed. There are certainly multiple other ways to do it. I encourage you to, if you have a different way, please, that would be fine. I'm just showing you what I would do, how I would find it. So all I know is where my center is and my vertex. And I encourage you to start building your equation. Right? Start building it. I know the center, so I at least have this part minus this part equals 1. I may not know the denominators yet, but at least I have this part. Right? Sometimes on a quiz or a test, students might just kind of not put anything down there. And that really would be better if you at least built the scaffold. At least you get some partial credit for building parts of your equation if you can't figure out every single thing. So I would encourage you to go ahead and build your scaffold before your equation, your template, before you have all the information. Okay, so we really just have this slope to go on, this 1 over 2. We know that this is the rise and this is the run, but I mean, I could just kind of say, oh, well, I know that that's a 1 and that's a 4 and just be done with it, and it wouldn't be right, would it? I mean, because it could be 1/2, it could be 2/4, it could be 3/6. I mean, we don't know what it actually is. So we need to figure that out. This is how I would figure it out. There are other ways, but what I would do is I would do it, I'm real visual, so I would do it graphically. I would start here at the center, and I would just follow my slope. I would go down 1 and over 2. Then I'd go down 1 and over 2, and then down 1 and over 2, and down 1 and over 2 until I lined up with the vertex. Why would I want to line up with the vertex? Because that's how we're basically building our asymptote, right? Isn't this the asymptote? Isn't that the asymptote that goes through the corners of the box, right? That's what I'm doing. I'm just kind of seeing where would the asymptote be? Well, it would be right here, right? And when it passes under the vertex, that's basically the end of the box, the rectangle. And so I would look at this height right here, and that height is 4. So that means I know that this distance is b. It's b. It's part of my conjugate axis, right? It's half of my conjugate axis. So that's how I would do it. That's how I would figure out what this fraction was. So the fraction actually is 4/8, right? It's 4/8. So 4 would be the number under my y squared. So 4 squared is 16. And 8 would be the number under my x squared, and 8 squared is 64. And that's how I would get the rest of that. Okay, are we okay with that? Okay, any questions for me? Okay.